Hello everyone, today we will try to understand the different types of parametric and non-parametric tests, and also what is testing hypothesis, and lastly we'll learn a little about ANOVA. So to begin with, let us try to understand the basic differences between a parametric and non-parametric test. So the starting point of difference is in the distribution pattern. While a parametric test relies on a normal or Gaussian distribution pattern, a non-parametric test is not really concerned about the distribution pattern, so it could be any. And when talking about normal or Gaussian distribution, let's have a look how typically a normally or distributed data set would look like. So it should look somewhat like the line shown in black, which is symmetrical, and the ones in red and green that are shown are the distribution sets which show kurtosis in them. So the green one is supposed to be a platykurtic data distribution pattern, and the red one is a leptokurtic one. In either of these cases, it is not a suitable distribution pattern to perform parametric tests with, because kurtic distribution patterns often tend to exclude the extreme regions from the distribution tail. So also, a normally distributed curve should have no skewness. So skewness could be either positively skewed or negatively skewed. So coming back to our normally distributed curve, we can run a couple of statistical tests to check if our data set is normally distributed. Like for example, we can test our data set with the Shapiro-Wilk test, or the Kolmogorov-Smirnov normality test, or the Anderson-Darling test, or the D'Agostino-Pearson's omnibus normality test. But while I'm sure that the Shapiro-Wilk test and the Kolmogorov-Smirnov normality test have been around for quite a long time, and these are very commonly used, but you'll find the other ones in different softwares as well. So returning back to our table of difference, the second type of difference relies on the data type that we're dealing with, while a parametric test works best with quantitative variables, which can either be in the form of ratio or internal. So these are numerical values, and these are quantitative in nature, while a non-parametric test works best with ordinal variables. So ordinal data types are variables which have ranks assigned to them. Like to cite an example, you can have grades A, B, C, D, and the ones acquiring, say, grade A, you have assigned the numeric value 1, for B 2, and C 3, and so on and so forth. So while you have assigned rank to these data sets or data types, but you cannot perform arithmetic functions with an ordinal variable. And the other one here is the nominal, also known as categorical variable, which do not have any numeric value associated with them. So to give an example of nominal variable would be, say, gender, ethnicity, eye color. The last point of difference, major difference between parametric and non-parametric measure, would be in the type of central tendency measure these tests are dependent on. So while a parametric test is a test of mostly tests for difference of mean, a non-parametric test almost always tests for difference in medians. So moving ahead, we now look at the different types of parametric and non-parametric tests that are commonly performed. So in the left side, you have the different types of non-parametric tests, and on the right side, you have the equivalent parametric counterparts. So if you were to perform a z-test or a one sample t-test or a pair t-test, which is basically comparing a specified value with a mean to test for difference. The equivalent non-parametric test would be the Wilcoxon sign test, and if we were performing, say, two independent sample t-tests, which basically compares two means, then the equivalent non-parametric counterpart would be the the Mann-Whitney test. And if we were to perform a one-way ANOVA, which compares three or more means with one variable, the equivalent non-parametric counterpart would be the Kruskal-Wallis test. And when we were to perform a two-way ANOVA, which compares to three or more means with two independent variables, the equivalent non-parametric counterpart would be the Friedman test. And if we were to perform, say, a correlation test, then the parametric test for the same would be the Pearson's coefficient of correlation test, and the non-parametric test for the same would be the Spearman rank test. And if we were to perform, say, a survival function test, then the log rank test comes into function. Well, I'm not very sure about its equivalent parametric counterpart. And the same goes for chi-square test. It is a non-parametric test which is usually used to test for independence of two variables and also for determining goodness of fit. So before performing these tests, you should always check if your data set is normally or non-normally distributed. So moving further, let's understand hypothesis testing and directionality of a test. Every time we run, say, a test, it could either be one-tailed or two-tailed. Suppose you're running a two-tailed t-test. So while for a two-tailed t-test, so the software will assign critical regions at both the tails of our distribution curve, and say we are interested at seeing a level of difference significance at the level of significance, say 5% alpha. So the software will assign 2 into 2.5% regions, that is the 5% significance region would be split into two 2.5% regions, and these would be assigned each at each end of the distribution tail. So every time we are running a two-tailed test, the statistical test would check for difference at both the ends, and these tests are usually performed when we don't have a pre-existing idea of directionality. We are not concerned with, say, if it is, say, greater than or less than, but we only want to know if there is a difference among the groups or distribution sets that we have. So to summarize, if we are performing a two-tailed test, say at 5% level of significance, 2.5% regions of the tails are assigned, and values falling in this critical region at the two ends of the distribution curve determines whether we reject or accept the null hypothesis. So if our values fall in this critical region, it results in rejection of null hypothesis, or alternatively acceptance of alternative hypothesis. And also it helps to remember that since a two-tailed test considers both the tails of the distribution pattern and is non-directional in nature, it is an ideal test for finding a significant difference between multiple groups when we don't have a pre-existing idea about the directionality, which is usually the case in a lot of researches. So in a lot of research work, we don't really have an idea if there is a sense of directionality, so it is safe to perform a two-tailed test in those cases. So for these tests, the null hypothesis should be there is no difference or the effect is zero, while the alternate hypothesis would be that there is a defect, there is a effect, or there is a difference, or the effect is not zero. But it shouldn't be like it is greater than zero or it is less than zero, because we are not checking for directionality in a two-tailed test. But say if we are performing a one-tailed test, so a one-tailed test could either be left-tailed or it could be right-tailed, but not both. And also it helps to understand that if we are performing the same test at, say, the same test at the same level of significance, that is 5%, the software would assign a larger region, because all the 5%, the critical region is assigned to only one end of the tail, which means that the chances of getting of reaching this critical zone is higher when we are performing a one-tailed test as compared to a two-tailed test, hence giving more statistical power to a one-tailed test. So to summarize, for a 5% level of significance, a one-tailed test would assign the entire 5% region to one tail of the distribution curve, and values falling in this critical region are considered to be statistically different and results in rejection of null hypothesis, and chances of ending in the significant region or this critical region is higher since it only considers one tail at a time. One-tailed test is used when a sense of direction already exists. So our null and alternate hypothesis for a one-tailed test could be like two ways. So in the first case, it could be like if we say that the effect is less than or equal to zero, the alternate hypothesis would be that the effect is greater than zero. Or if we say that the null hypothesis is the effect is greater than or equal to zero, so for which the alternate hypothesis would be that the effect is less than zero. So now that we are done with understanding the testing hypothesis and the directionality of a test, we move forward with ANOVA. ANOVA, or also known as analysis of variance, or also known as Fisher's analysis of variance, is a test which compares variables, can be one or two, with multiple uh, groups. The differences between means in multiple groups are compared with one variable or two variable, as may be the case. So at the very basic level, ANOVA is a special extension of TNZ test, and also the name says that it is analysis of variance. Don't be misled. It assumes homogeneity of variance, and it tests for difference in means between multiple groups. ANOVA is performed to test if there is a difference between study groups. So when you're performing a software test, it will usually return F values, and while it will directly also tell you whether your test difference is significant or your interaction is significant or not, it will also return you the F values, which are based on degrees of freedom. So it considers the numerator degrees of freedom and denominator degrees of freedom, based on which the F value is calculated. So if the F value returned after the test run is 1, it signifies that our null hypothesis is true, so it leads to rejection of the alternate hypothesis. But this is not too much worrisome. You need not worry too much about how should you interpret the F value, because most of the softwares give you direct differences and p-values, and if the interaction is significant, the groups itself are significant, the differences in groups itself are significant, the interaction is significant or not. So ANOVA could be one way or two way. So for a one-way ANOVA, we have one factor or variable and multiple groups, uh, and one-way ANOVA could also be independent or unpaired, and it could be matched or paired. And if we were to cite an example for a one-way ANOVA, so it would be like comparing the effects of 5 different drugs. So you have, say, 5 drugs, say D1 to D5, and you have a set of values that you have obtained after treatment for each of the drugs that you perform treatment with, and you want to compare if there is any difference between the drug treatments. So here there is only one variable factor, that is the drug, and and you have multiple groups of data sets, so you would be comparing the difference in means between these multiple groups. So you would be performing a one-way ANOVA. And if you are, say, another example would be like if you have, say, only one drug, and now this time you are doing the treatment with 5 different cell lines, and you want to study if there is any difference in treatments in between the cell lines, the effect of treatment in these separate cell lines. So again, you would be performing a one-way ANOVA. So moving on to two-way ANOVA, this deals with two independent factors or variables and interaction with multiple levels or groups as earlier. This also could be independent or paired or matched. So giving example would be like, we take the example of the previous case where we were doing uh, we were doing a drug treatment of 5 different cell lines, but this time we, along with the drug treatment, we have an inhibitor also. So now we have another variable added here, that is the inhibitor. So in this case, you would perform a two-way ANOVA. And another example would be like if you have subjects or patients and they are undergoing, say, 3 or 4 types of treatment at one hospital, and then they are undergoing the same or very similar treatment at, say, hospital number 2. So you have, say, the two variables here would be the hospital number 1 and hospital number 2, and hospital number 3 could be. And the second variable here is the different types of treatments that are common at your 2 or 3 hospitals. So the variables here are the treatment type and the hospital. And not only in this case you would perform a two-way ANOVA, you would also perform a two-way ANOVA which is matched, because your patients are matched in this case or are paired. Although I have only mentioned one-way and two-way ANOVA, you would also find in some softwares the options to perform a three-way ANOVA, which is an addition to the two-way ANOVA, addition of another independent factor. So the softwares that are commonly used to perform ANOVA are SPSS, Minitab, R language, and GraphPad Prism. So to conclude, ANOVA helps us to perform quick analysis on multiple groups, and also to recall, this can be done with independent t-tests on multiple groups, taking 2 at a time, but this would lead to an inflation of the type 1 error. The type 1 error is basically the error of positive acceptance of false positive acceptance of alternate hypothesis, or wrongful rejection of the null hypothesis. So with ANOVA, this type 1 error is greatly reduced, so it is always a better option to perform ANOVA over independent t-test on multiple groups. So it helps to remember that ANOVA it works best if the sample set is homogeneous in nature, and there shouldn't be missing values, especially if you're performing a two-way ANOVA. And to conclude, ANOVA works best with Gaussian distribution. And that's all for this video, and goodbye until next video. If you found this video helpful, I would love to hear your feedback in the comment section. Thank you.